Hey, what's happening? Today we're going to do some stuff with graphs, and we'd like to look at a lot of definitions and check out some properties of graphs. Here's our definitions. Many of these you already know. We're going to cross this one out and this one out, and we'll call this odd and this one even. Function. FXN just for short, okay? Function. Because I repeated that, I'm sorry. Okay, the domain, all x values. The range, all y values. And maybe we could say mapped. The ones that are used, okay? The x-intercept. This occurs where the function is equal to 0. It's where it crosses the x-axis. The y-intercept is what happens when x is 0. That's pretty cool. So if you put 0 into the function, that will give you the value of your y-intercept. Okay, origin symmetry. Well, it's what it sounds like. And it basically says if you reflect the graph through the origin, so let's say I have this guy here, and that's all I have. If I reflect it through the origin, my new points would be here, and this high point here would be maybe here. This point all the way over here would go down, over, down. Okay, so I'm probably drawing this very wrong, but it would be something like that. Reflecting everything through the origin. Well, as you can see, since the graph was only here, and when I reflected it through the origin, it ended up in the third quadrant, it didn't exactly lay on top of itself. It actually created a new graph. That's not symmetric. Here's a picture of something that actually has origin symmetry. This guy. If you reflect it through the origin, it would land right on one of the points on this side. It would basically map onto itself. Now here's something else you can do. Oh God, not that. Hang on. There we go. You can do this. If you rotate your graph 180 degrees and it looks exactly like it started, which this one obviously doesn't. Ha, now it does. Then it's origin symmetry. So that's just a little trick, okay? Rotate it 180 degrees to the left, and if you're looking at the same picture, you've got origin symmetry. Rotate 180, and it's the same. Nice. Y-axis symmetry. Okay, well that one is just, can you fold the graph in half and you're looking at the same exact graph? You know, like it maps onto itself. I'll give you an example of that right here. The good old-fashioned parabola definitely has y-axis symmetry. This is the y-axis. If you reflected every single point across the y-axis, you would land right back on top of the graph. That's symmetric. Something like this is not, because if you reflected this on this side of the graph, it would land there. And that certainly wouldn't map onto itself. It would actually create a whole new graph. Reflection in y-axis maps onto function. Cool. Okay, so origin symmetry, cross that out. Now, neither symmetry is quite obvious. It's not origin, not y-axis. It's anything else, okay? Now, this odd and even function business, this is pretty cool, and we will spend more time on this later, different videos. To be an odd function or an even function, you can tell just by looking at a graph. And here's the rule. And it's nice and easy to remember because odd starts with an O, and you are an odd function if you have origin symmetry automatically. I don't know if there's two M's, but I'm sticking with it. Okay, is there? Yeah, there is. Good. Even function. You are an even function if you have y-axis symmetry. Don't worry about what that means right now about being even and stuff. Just know that you're even if you're symmetric with y, you're odd if you're symmetric with the origin. Cool. And behavior. And behavior says, what is the graph doing as it approaches positive and negative infinity? So what is graph doing as x approaches positive and negative infinity? I'll show you a picture in a minute and you'll know what that means. Relative minimum. Let's just write any low points with a question mark. Or how about slash turning points? And the relative maximum, same thing. Are there any high points? Or turning points? Okay, very cool. That's a lot of notes. I appreciate you taking all those. I'm going to move on. If you didn't finish them, just pause the video and catch up, okay? This is what we need to be able to do. We're looking at this graph. Let's fill out all the information on the right. So domain, we agree, is the x-axis. Now, a couple of things to note. This goes on forever. This goes on forever. So what values on the x-axis are mapped? Well, all of them. I mean, if I went to 2.5, there I am up here on my graph. If I went to 3, there I am on my graph. If I went to 3.5, I don't know, I'd be somewhere up high off the chart, but I'd be there. So you have to realize that this arrow means that it's going up and to the right forever, and this is going down and to the left forever. So all of the values on this x-axis will be part of some coordinate on this graph. Like, I don't know, -5 is certainly going to be pretty low, right? So maybe it would be like -5, comma, -10,000. I don't know how low it is when it gets to -5 because it's going down so fast, but it will get there. And that's what you need to know. These arrows mean they go forever, down, to the left, up, and to the right. So when you say domain, we're going to say soft bracket, -infinity, +infinity. The range, -infinity, +infinity. Because it's going up, so all these y values will be part of some points, coordinates, right? And all these y values will exist over here. So it's infinity, infinity. Are there any x-intercepts? Absolutely. This is the x-axis, right? We have them at -2, 0, and 2. Set notation, -2, 0, 2. Any y-intercepts? Yes. At 0. Relative minimum, relative maximum. So what we're talking about there is any kind of turning points that give you a low spot on a graph or some turning points that give you high spots on a graph. So check this out here. This, I think, is a low point, right? It's not the absolute low because that's infinity, -infinity. But this graph does have this thing that we call a relative minimum. Relatively speaking, this is a very low point on this graph. And then, of course, up here, you would call that a relative maximum. You know, it's not the most high point of the function. That's somewhere up in infinity over here. But it's definitely a relative max. It's got this turning point business. So the relative minimum, let's estimate, occurs at x equals 1. And the relative maximum at -1. Does this have any kind of symmetry at all? And I think you would agree it has origin. If you turn this thing over 180 degrees to the left, you'd be looking at the same exact picture. So what does that mean? It means it's an odd function. Now, what's the degree of this? You really don't know. I'll be honest with you. You really don't know. But you do know the minimum. You do know the minimum. How many real roots does this baby have? 1, 2, 3. 3. So I don't know if there's 3, if it's like x to the 3rd. I don't know if it's x to the 5th, and so on and so on. Because you never know how many imaginary roots there can be. And at the beginning of this packet, we said imaginary roots come in pairs. So even though there's 3 that I can touch, if there happens to be any imaginary solutions to this polynomial, they would come in pairs anyway. So you'd have 1, 2, 3 real guys, and maybe 2 imaginaries over here. Maybe 2 imaginaries over here. Who knows? There's really no solid way to tell for sure. So what do we mean by degree? Let's say odd. That's going to be very important for us later. So let's call this not an odd function. Don't confuse that. But it's definitely an odd degree. It's odd. Okay, what are the roots? The roots occur at x equals -2, 0, 2. Now, here's the part that's important. Where am I increasing? Where am I decreasing? When we judge increasing and decreasing, we judge it from left to right. So in that direction is how you can tell whether a graph is increasing or decreasing. Just like you read a book, from left to right. So what I'd like you to imagine is that here you are walking in this direction from left to right. When will you be walking up a hill? When will you be walking down a hill? When will you be walking up a hill? Okay? If you think of it that way, you'll never go wrong. So, for what x values am I increasing? Now, let's agree, because this is a horrible picture, let's agree that this is -1 right there, and that this is +1. I know it's a little bit off, but let's just say that to be nice and easy, okay? So I am increasing from -infinity, and I'm stopping to increase probably at -1. Now, super important right here, soft bracket, my friends. Soft bracket. Why? Because you are starting to decrease from -1, and you stop decreasing and start climbing the hill again at +1. So, you can't put a hard bracket here on -1 because you're going to need to use the same number here, and you can't be increasing at -1 and also decreasing at -1. It's a pretty intense topic, but ladies and gentlemen of the jury, at this very point right here, that turning point, your slope, the line tangent to that point, is 0. 0 slope. So at 1, let's say right here, right? At this value 1, you can't be increasing or decreasing. You're at that very moment turning around. You're flat-footed. You have no slope whatsoever. Okay, really, really important. Now, sorry, I took a tangent there. No pun intended, but it's really, really critical that you know that. Soft bracket. Okay. Let's see, what else are we doing? Oh, I'm also increasing here, my last piece, right? So let's add to this increasing business. Let's go color blue, and we'll say union all the x values from 1 with a soft bracket to infinity with another soft bracket. And you know you always do soft bracket on infinity because you can never equal infinity. That would just be a miracle. Okay, so that was that. That's basically the topic. I mean, we're going to do another example, but if you get this, you've got it all. This is interpreting graphs, So just be on the lookout for this. Odd, even functions are different than what kind of degree do you have, odd or even, okay? One stands for the exponent and the other stands for something completely different. This is cool because it has a couple of relative maximums here and here. It's got a relative minimum here, right? Video. Here's an even degree, like x squared, right? That's even. And isn't that what this looks like? It's a parabola. It's an even degree. The arrows are pointing up, the arrows are pointing down. Now, end behavior is for an even degree positive coefficient as x approaches infinity, which is this way. Look at what your graph is doing. It's approaching positive infinity. And that's what this statement says right here. Fancy, isn't it? But that's all it means. This is saying as x approaches negative infinity, so as your graph goes to the left to negative infinity for x, what's my y values doing? They're also going to positive infinity. So if you have a negative coefficient and you're even, it's just the opposite. As x goes to the right, your graph goes down, negative infinity. As your graph goes to the left, your graph also goes down to negative infinity. So get used to this. We'll see this in our class a lot. And finally, for those oddballs, right? Check this out. Here's a little squiggly wiggly. There you go. For odd degrees, as x goes to the right, so does your graph. As x goes to the left, your graph goes down. That's if the leading coefficient is positive. If your leading coefficient's negative, like you see here, as your graph goes to the right, your graph goes down. And as the x values go to the left, your graph goes up. That's what this fancy stuff means. Okay, so that was a look at graphs and some of their key features and what happens on the tails and what does it mean to be even and odd, all that stuff. I hope you enjoyed it. Sorry if it was a little long, but we did have a lot to cover. Have a great weekend, and Zamfini and I will see you on Monday, Halloween. Bye-bye.